In the second part of chapter 10, we are going to be looking at comparing two means. So that means we're going to take two samples, one from two different populations, and try to say something intelligent about the means of those two populations. Are they the same? Are they different? And what do they differ by? So we're breaking this section up into three sets of notes. Today we're going to go through an example, so a simulation, and then we'll talk about what the shape, center, and spreads are for the sampling distribution of the difference in two sample means. And then we'll start looking at some conditions. All right, so what we want to do here is we want to compare the means from two different populations. So we have population 1 and population 2. And so we're going to take samples from both those populations and compare the sample means and then try to use that information to say something intelligent about the difference in the population means. So our parameters of interest are the population means mu sub 1 and mu sub 2. The best approach to taking separate random samples from each population. Um, and then we're going to compare the sample means. So we are going to, by looking at how different the sample means are, we're going to try to say, well, what's the likelihood that our population means are a set distance away from each other. All right, suppose that we want to compare the average effectiveness of two treatments in a completely randomized experiment. We use the mean response in the two groups to make this comparison. So sometimes we'll be taking samples from populations, sometimes we'll be subjecting two groups to different treatments in a comparative experiment. All right, so this table sort of visualizes what's going on. So we're either going to have two populations or two different treatments, right? So treatment 1, treatment 2, population 1, population 2. And then there's going to be some sort of measured parameter. It could be, if it's an experiment, that would be the mean number of headaches, after taking the medicine in treatment 1 versus treatment 2. So it could be the measured response, or it could be of some sort of measure of a parameter, from that population, some kind of measured value. And then we'll be looking at the mean from both those populations. Now, we won't know, though. Those, again, mu sub 1 and mu sub 2 are theoretical. And then we'll get the statistic either from the treatment groups or from the sample from the population. And so that'll be x bar sub 1, x bar sub 2, and then the two sample sizes, small n sub 1 and small n sub 2. All right, so let's look at an experiment here. So 10 strips of polyester, pieces of cloth, were randomly assigned to two groups. One group was buried in the ground for 2 weeks. The other was buried in the ground for 16 weeks. Okay, after unburying the strips, so after pulling them out of the ground, each was put into a device that pulls it apart and measures how many pounds of force are required to tear the material. All right, breaking strength is a good indicator of decay in this case. So we can see that we have 5 of the amounts up here were in group 1, which means they were buried for 2 weeks. And then 5 amounts here, 5 different pieces of cloth were in the group 2, which were buried for 16 weeks. So then they were torn apart. So these numbers represent the strength required to pull apart the samples and the sample cloths. And so higher number means less decay. Smaller numbers mean it was easier for it to pull apart. All right, and so what we did is in each group was we took the sample, we took the average strength. And so we could plot those 10 data values on the dot plot as well. Um, And so that's what's here. And so we will be subtracting the x bars to get the sample, the difference of the sample means. And we can see visually, group one is the upper group, and group two is the lower group. You can see that group one indeed does have a higher breaking strength. All right, it's the group that was buried for 2 weeks, and the group two, buried for a longer time, took less force to tear them apart. And so, what we want to think about is how likely is it that we could have gotten that difference just by chance alone, by random chance? So the difference we saw in the two experimental treatment groups was an average difference in the averages of 7.4 pounds of force needed to tear apart the samples. So could we have gotten that just by chance alone? Is really what we want to explore, or in this case, we're going to simulate. All right, so what I've done, and if you're doing this at home, you could take 10 identical pieces of paper and write the 10 results we got. So what we're going to assume, we're going to sort of play devil's advocate when we want to call into question the results of an experiment. So we want to assume that the breaking strength for each piece of cloth, each piece of polyester, was not dependent on how long they were buried. The length of time buried had no effect. And so, the cloth that broke with 98 pounds of force broke at 98 pounds of force and would have broken the same whether it was buried or not buried, right? So that burying it for a different amount of time really didn't affect the breaking strength. And so just by dumb luck, more of the stronger pieces of cloth that took longer to took more force to tear got into group one than we saw in group two. And so what we're going to do is if we're in class, we're going to hand out decks of cards, little square cards. At home, you would possibly make 10 pieces of card if you want. And put these 10 numbers on them, and then you can sort of simulate what we're going to do. All right, so in class, everyone has I'm going to give each group of 2 kids a pack of cards, pack of 10 cards. Now, these are not playing cards, they're just like little squares. And so you're going to take your pack and you're going to mix them up. It's hard to shuffle these. They're square. They're not really like a deck of cards. So shuffling doesn't really work too well. So you turn them upside down on your desk and kind of like slide them around, right? Mix them up. And then break them into 2 groups. So 2 groups of 5. So one group is going to be considered group 1, and the other group 2. And then we're going to turn them over. And so then we'll turn them over and we'll take the average of each group. So group 1, which is the group that would have presumably been buried for 2 weeks, and group 2 is the group that would have been buried for 16 weeks. And so could we get a difference? Again, it's not really going to matter. This is what we're assuming, that the length of time buried doesn't matter, that the strength required to tear each piece of cloth is unaffected by how long they were buried. And just by dumb luck, we got pieces of cloth that took more force to tear in the treatment group number 1. And so how likely? So this is going to these assignments were just by chance alone. Okay. And so we'll calculate the X bars for each group 1 and group 2. And then what we'll do is we will subtract those 2 means. So the mean X bar from group 1 minus the mean X bar from group 2, and we look at those differences. And so if we were in class, I would have each group do several simulations of this, and then you would yell out the X bar sub 1 minus X bar sub 2 difference that you got in your simulation, and then I would plot those. All right, so here are the plots for 119 simulations. And you can see here that it does seem like they're centered at 0, which is kind of what we would expect. If there really is no difference, we would expect this to be set at 0. Now, that's the center of our distribution, but that's not evidence that there is no difference, right? Because our simulation, right, is assuming that there is no difference and that was just by chance. And so we ordered them. So it makes sense that our simulated dot plot is centered at 0. All right, so but how likely are we to get the difference just by chance alone? How big the difference that we found in our experiment? So the difference we found in our experiment was 7.4 pounds. And so then we say, well, how likely is that to occur? And so if we look, there were about 17 simulations that had a difference of 7.4 pounds or more. And so what kind of a probability is that, right? So just by chance alone, we'd expect the difference x bar sub 1 minus x bar sub 2 to be equal to or greater than 7.4, 17 out of 119 times, or about 14% of the time, we would expect a difference as big as this or bigger, about 14% of the time, just by chance alone. So that seems like a pretty big probability. So that is actually evidence to support the fact that this could have happened just by chance alone. And as a result, this sort of supports the idea that there really is no difference, that the difference we found could have come about just by chance alone 14% of the time. So this kind of supports that the difference between the two populations or the two different treatments is probably 0. There's not strong evidence against that. All right, so let's look at another example. And in this example, we're going to demonstrate the shape, the center, and the spread for the sampling distribution of the difference in the X bars. So to explore the sampling distribution of the difference between two means, let's start with two normally distributed populations having known means and standard deviation. So again, we're going to assume for this example that we know population parameters, the mean and standard deviation. So mu and sigma for two different populations. So based on the information from the U.S. National Health and Nutrition Examination Survey, the heights in inches of 10-year-old girls follows a normal distribution, and that distribution is 56.4 inches with a standard the mean of 56.4 inches and a standard deviation of 2.7. The heights in inches of 10-year-old boys follows a normal distribution. Its mean is 55.7 and a standard deviation of 3.8. So girls are a little bit taller than boys, and their heights vary a little less than boys. So boys, they vary a lot more in their heights than the girls do. All right. Suppose that we take an independent sample, an SRS, of 12 girls and 8 boys of this age, and we measure their heights. And so what we want to think about is what can we say about that difference, the sample, the difference in the sample means for girls and boys. So we designate that as X bar sub F for females minus X bar sub M for males. So females and males. All right, so we have here some approximate sampling distributions. One on the left is for the females, and one on the right is for males. And you can see they're both approximately normal. And the approximate sampling distribution appears to be centered pretty close to the mean. And we would expect the actual sampling distribution to be centered right at the population mean. And then the spread, again, this is the sampling distribution. So we would take we would take the sigma and divide that by square root of n. And then the same thing for the boys. Boys, standard deviation is a little bit wider and there's fewer of them. So the sampling distribution will be wider as well. All right. Now, if we take, and instead of plotting each female X bar and each male X bar in the simulation, we did this 1,000 times. What if we took, when we got the X bar for the female and an X bar for the male, instead of just plotting those independently, we subtracted them first and then plotted them? That would be this third graph that we're about to reveal here. Okay, so that would be, and again, 1,000 of them. So even though there were fewer boys than girls in each of their samples, they still each did 1,000 samples to generate these sampling distributions. All right, so you can kind of assume, I think the assumption is that if the two sampling distributions, one for females and one for males, those are both normally distributed, that the difference will also be normally distributed. And we see that will be the case. So it's normally distributed. Where's its center? Its center is actually at the difference in the two mu's. The mu female minus mu male will give us the mean of our sampling distribution, which is 0.68, 0.67. And then notice that the standard deviation of the difference is more wide, right? The standard deviation is larger. It's more varied, even though we are subtracting the two data values to sample means. The resulting sampling distribution of the difference in X bars is more varied than either one of the other ones, right? And so remember that we are not, to get this value, the standard deviation of the sampling distribution of the differences, we don't add the standard deviations instead. We don't subtract them like we do with the means. What we do is we add variances. So remember that we're adding variances here, and that's how we get that standard deviation of the sampling distribution of the difference in X bars. And that sort of is demonstrated here. You can see that in order to get the new variance, we add up the variances of the other two. So we're going to, so what we're going to do is look at here. This is the standard deviation of the sampling distributions for each of the individual samples, and then it's the square root of the whole thing. So we squared the original ones, right, to get this fraction under the square root, and then we have the other variance of the sampling distribution, and so we add those up, and then we take the square root of it to get the standard deviation. Okay, so let's just go through this. So talking about the shape, we know the sampling distribution of the difference in X bars is going to be approximately normal if we know that the two sample sizes are greater than 30, right? So in other words, the central limit theorem is going to tell us that each of the individual sampling distributions is normal if each of their sample sizes is over 30. So then the difference will also be approximately normal. The mean is simply going to be the difference in the two population means. And then the spread, or the standard deviation of the sampling distribution, is given with this formula, assuming, of course, that we've checked our 10% condition. Now, we'll deal with the fact in a second that we are not going to know sigma, and what do we do in that case? All right, so here we have a visual of the sampling distribution of the difference in means. We talked about how the center of it is the difference in the mu's, and we just talked about the standard deviation of the sampling distribution is using our two sigmas and our two sample sizes. All right, so let's look at an example and practice a little bit of some of the shape, center, and spread of our sampling distribution. So, potato chip manufacturer buys potatoes from two different suppliers, Riderwood Farms and Camberley Incorporated. So the weights of the potatoes from Riderwood Farms are approximately normally distributed with a mean of 175 grams and a standard deviation of 25 grams. So again, we're pretending we know the population mean and the population standard deviation. For the time being, we're going to pretend we know those. The weights for the of the potatoes from Camberley are approximately normally distributed with a mean of 180 grams and a standard deviation of 30 grams. And again, we're assuming we know the population parameters there as well. All right, when shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment, and then they weigh them. All right, let X bar sub C minus X bar sub R be the difference in the sample mean weights of the potatoes from the two suppliers. So the first question is, what is the shape of the sampling distribution of the difference in X bars and why? So write that down, pause the video, write that down. All right, so we know that the shape of the sampling distribution of the difference in X bars is going to be approximately normal because the sample size, the sample size was not big enough, but because we were told that each of the population distributions was normally distributed. So we don't need to have a sample size over 30 in this case. We know each of the sampling distributions is approximately normal, so therefore the difference, the sampling distribution of the difference in X bars will also be approximately normal. All right, find the mean of the sampling distribution. Pause the video and then write it out. Okay, so the mean is simply the difference in the population muse. So that's 180 minus 175. Now, it's kind of important that you set up which direction you're going, right? So if you had done it the other way, then your answer would be negative 5 grams, which is fine, but you just have to be consistent in the way you set it up. So here we set it up as X bar sub C minus X bar sub R. So the Camberley's farm minus a Ridgewood farms. But if you reverse that, that's fine. But you just have to be consistent in all your work. You can't flip flop halfway through the problem. All right, and then part C, find the standard deviation of the sampling distribution of the difference in X bars. Pause the video, write that out. Okay, so we're using our formula here. Sigma squared over n plus sigma squared over the other n, and then the square root of that whole thing. And that gives us 8.73 grams as our standard deviation of the sampling distribution of the difference in X bars. Okay, so when we have two different samples from two different populations, we know that similar to what we saw when we were taking one sample from one population, we had a t statistic, and we're going to have a similar, we're going to use t rather than z. Remember, t means that it's a t distribution rather than a z distribution, which is the standardized normal curve. If the 10% condition holds, we know the sampling distribution of the difference in the X bars is going to be this formula. However, we're going to see in the next slide that we're not really going to know sigma sub 1 or sigma sub 2. We don't know the standard deviations of the two different populations. And so it is going to, we are going to have to use our S's, our standard deviation of the samples, as a substitute. We'll see that in the next slide. So that is what's going to make us use a t distribution. So the sampling distribution of the difference in X bars is normally distributed, but once we make that substitution of S for sigmas, then that sampling distribution of the difference, we're going to find that that is a T distribution, just like we saw with one sample from one population. All right, so here we again call it the standard error, S sub 1 squared over n sub 1 plus S sub 2 squared over n sub 2 would be the variance, and then we would take the square root of that to get the the approximate standard deviation of the sampling distribution. So we'll call that the standard error. And that substitution is for S, S's go in for sigmas because we don't really know the true parameter sigma values from the two populations. That's what causing us to use a T distribution. So that S, those two S's, are what now takes our sampling distribution of the difference in X bars and slightly changes it from normality to a T distribution. All right, so the two sample T statistic has approximately a T distribution, again, assuming normality is true for these for the two independent populations, or that the central limit theorem holds. So we also need to think about, okay, the degrees of freedom. So the degrees of freedom before were was just n minus 1 was the degrees of freedom, but now we have two different sample sizes, so the degrees of freedom is much more complicated. All right, so to calculate the degrees of freedom, we would use this formula. So for obvious reasons, we're not going to use this formula. It's way too complicated. So there are two options that we're going to use. So the first one is use your calculator to do any calculations. So use your calculator to do the test that you want. And as a result, your calculator will calculate the degrees of freedom. Often, the degrees of freedom will not be a whole number like we saw in the T table. And then so use technology if you have that option. The other option is if you don't have technology available, or the way the problem is written, you can't really do a test in your calculator, then we simply use either n sub 1 minus 1 or n sub 2 minus 1, whichever is smaller. So the sample sizes are not always the same. Often they should be, similar, but they're not always going to be exactly the same. And so we take the smaller one and subtract 1 from it. Okay, so this will cause the confidence interval to be a little bit larger, right? Larger, as large as or a little larger than needed. And then so you're more likely to capture the true difference. And then for a test, a hypothesis test, it's going to result in a p-value which is equal to or a little bit larger than the true p-value, by using this option 2. And so then we'll be a little bit more likely to reject H naught. So it's more considered a more conservative approach. So because we're using the smaller of the two degrees of freedom from each of the samples, the result will be a little bit more conservative. All right, so some conditions that we have to check. The same kind of conditions, but a little bit more detail, and a little different now that we have two different populations. So we want to make sure that we're talking about the data coming from two independent random samples or two groups in a randomized experiment. But don't just say the data was random, right? So talk about the fact that you took two independent random samples from two different populations, if you are sampling. Otherwise, you're using a randomized experiment. The 10% rule makes sure that you're not sampling more than 10% of the population in either case, right, from either population. And then the large count condition. So if both population distributions are normal, or if the sample sizes for both samples are over 30, then we know then we have an approximate sampling distribution of the difference in X bars. If either population or treatment distributions are unknown shapes and the corresponding sample sizes are less than 30, then we would graph the data like we saw. But here we might have to make two graphs, right? A graph of the of both sets of sample data. So two box plots, for example. All right. And then for each of those, we're going to look for the same thing. Do we see any outliers? Do we see any strong skewness? So still sort of three situations here, right? If we know the both population distributions are normal, we're good to go. If both sample sizes are over 30, we're good to go. And then if we don't know anything about the population distribution being normal, and the sample sizes are under 30, then we would graph both of them. I suppose if you had one that was over 30 and one that was under 30, we would just graph the data that was under 30. But more often than not, they're either both sample sizes are going to be under 30, or both are going to be over 30. We usually don't have varying different sample sizes. All right, so your homework due next class is 31, 32, 33, and 34. None of those are four-step problems yet. We'll get to those more in the next part of this section.